we'll get started. Okay. So previously we have seen how to write the Maxwell's equations in time domain, all right, and we also saw some similarities between the Maxwell's equations and telegrapher's equations. We classified the materials into different types. We also derived the wave equation, which looks very similar to the transmission line wave equation, right. And we saw about this direction of propagation, electric field being a vector, magnetic field also being a vector. Previously voltage was a scalar quantity, now we are getting used to this vector notation. And then we are also saying that the direction of propagation is z, that means that your electric field cannot have a component in z. Similarly, your magnetic field cannot have a component in z, so you have to get used to these things, right. And then we drew a table where there was a similarity between the Maxwell's equations and the telegrapher's equation. We saw that there is a one-to-one correspondence, all right, between the equations, the quantities, the solutions, all right, and also the interpretations. Okay. We also then modified the program. All the modification that we did was just modifying the variable names. We ran and it ran fine, all right, but the interpretations were slightly different. For example, in the case of transmission line simulation, you would have had voltage equal to 0 being short circuit. In this case, you will have to deal with electric field being equal to 0. That is a perfect electric conductor, all right. So the slight changes in interpretations, we touched upon them, all right. And we also briefly saw about characteristic impedance and or intrinsic impedance of the medium and velocity, and then we'll begin where we left off. Okay. So in this class, the idea is to introduce the concepts which are particularly different with respect to the electromagnetic waves rather than the transmission lines. And one of the things that we are going to be introducing is polarization. Okay. Previously, we saw that one of the key differences was electric and magnetic fields being vectors. That was one difference. Okay. Now we are going to go ahead and show what this polarization actually means. Okay. So we'll begin with where we left off and then proceed systematically towards the concept of polarization. Okay. Where we left off was writing the velocity of the electromagnetic wave. Okay. Okay. And it is denoted by the letter C. Previously, we had used U for the transmission line. Just to differentiate that we are talking about an electromagnetic wave, we just switched to a different variable, all right, and it turned out to be 1 by square root mu epsilon. Okay. And mu is for the medium, epsilon is for the medium. In case we are talking about vacuum, okay, we represent it with a suffix of 0, right, epsilon naught. Okay. So that is going to be equal to 8.854 times 10 to the negative 12 farads per meter, and the value of mu naught, okay, is going to be 4 pi times 10 to the negative 7 Henry per meter. If one has a look at the units, you will find out that this looks similar to L and C, the distributed L and C, okay, Henry per meter and farad per meter, all right. So there is a one-to-one correspondence, and for the case of vacuum, C naught is okay, is approximately 3 times 10 to the power 8 meter per second. This sets the upper bound for the velocity of an electromagnetic wave in the course that we are going to be studying, all right. In any other medium, we already discussed that in the denominator for the velocity, you will be expanding it for a homogeneous, isotropic, frequency independent medium, all right. We will be just writing this as a product of mu r, mu naught times epsilon r, epsilon naught. All of these are constants for a particular medium. And then we notice that epsilon r and mu r for any material medium are going to be greater than or equal to 1, which means that the velocity in any medium other than vacuum is going to be smaller than the velocity in vacuum itself. Okay. So the vacuum velocity sets an upper bound, which means that there is a maximum velocity. The velocity cannot be infinite once again, just like in transmission lines we talked about. Okay. We also briefly talked about the impedance. The characteristic impedance eta that we wrote down in the previous class was mu by epsilon for any medium. You can expand this to be mu naught mu r divided by epsilon naught epsilon r under a square root, all right. And in the case of vacuum, (377 ohms). You can also remember this as 120 pi. Okay. These are things that we have already seen towards the end of the previous lecture. We also had a short discussion about if the electric field is 1 volt per meter, the magnetic field is going to look like a smaller value in amperes per meter, all right. But that does not mean that the effects are going to be far lower or anything, depends on the material. And we said that this is one of the reasons why we ran the programs with relative units of mu r and epsilon r rather than mu naught and epsilon naught to avoid some zero approximation errors concerning the magnetic field. This is what we had talked about in the end of last class. So, we will begin where we left off. Okay. The first thing that we can start with is, now that there is a one-to-one correspondence, we can start to look at the AC excitation of transmission line analog in this case. So, if you have an electric and a magnetic field that has a frequency dependence, all right, and that what we mean to say is a constant frequency source of electric and magnetic field. Okay. Previously, we had a constant frequency source for a voltage that we will be considering as an AC source. Equivalently, here you will be having a constant frequency source of an electric and a magnetic field. Okay. So, we will begin with that. In the previous class already we were discussing about travel direction or propagation direction being z, we will retain the same. Okay. Okay. And in the previous class we had seen that the electric field cannot have a component in the z direction because it will not create a time varying magnetic field, it has to be Ex or Ey, and the previous class we had taken Ex to begin with, and we will retain the same over here. We will say that the field has an X component, so right, and X component only. Okay. Okay. If this is the case, the electric field, okay, in general is a function of both space and time, just like your voltage is a function of space and time. Previously we had written V of z comma t, all right. Here, just to be clear, because it is a vector quantity, you can always start with a general description of E and say that it depends on E, x, y, t, just to say that it depends upon space and time, all right. However, we know that with respect to x and y, there is no change in the value of electric field. That is how we had written the del cross E equation in the previous lecture. We had crossed out dou by dou x, dou by dou y, we retain only dou by dou z. So, E is a function of only z comma t, the manner in which we are considering this problem. So, you can always write this as it has Ex component which is a function of z, okay, pointing towards x direction, right. On top of that, we are introducing a time dependence which is going to be periodic, right. So, the time dependence we just write it down as e to the j omega t. This will have a cosine omega t plus j sine omega t. We can always write this down as e to the j omega t. Later on we can include only the real part for our analysis, and as we had discussed before, the advantage of using exponential expression for the trigonometric quantities is derivatives become easy to calculate. Okay. So, first what we can do is we can start by writing down the wave equation in the frequency domain, all right, or we can start to write the wave equation for the alternating source of electric field, right, similar to what we had written for the voltage. So, here once again to emphasize dou by dou x is 0, dou by dou y is 0. These are very well known now already in the class. Okay. So, we can start to write down the wave equation as notice that I have taken Ex of z e to the j omega t, all right, and I am just writing this down as d square e by dz square, assuming that there is a variation with respect to time, that is periodic. I have not written the e to the j omega t over here explicitly, but Ex of z should involve that also. So, if you want to be more specific, you can always write this down, left hand side and right hand side can be multiplied with e to the j omega t, and you will get the exact e of z comma t on both the sides. Okay. In the case of voltage, we had not considered this because with respect to time it is only periodic. Okay. If you know the time period, you can always calculate what is happening at any instant of time at a point in space. So, this would be the equivalent expression for the wave equation, all right, for an alternating source. And just like in the voltage case for transmission line, we will call this gamma to be a propagation constant. Okay. Now, the variable names are also not changing so much. Okay. Okay. And in this particular case, this omega is j omega square root mu epsilon. Previously, in the case of transmission line, you had j omega square root of L c. So, we are just replacing L with mu, c with epsilon, j omega square root mu epsilon. We already know from the transmission line case that this corresponded to a lossless transmission line. There was no R and G involved in that. So, in this case also it is the same. This is a lossless transmission line with no wires. We are dealing with fields, that is all right. And equivalently, we can say that this has j beta, where this is the phase constant. So, there is really a one-to-one correspondence, not much is changing other than changing variables with respect to transmission lines. Okay. Having written this, okay, it is a easy way to write down the solution. Now, looking at our previous notes, we can just write this to be Ex plus e to the minus j beta z plus Ex minus e to the plus j beta z. Okay. This is with respect to space. If you want to include the effect of time, all right, then you will just say that so, if you want to find out the instantaneous value of the electric field, you can always multiply it with e to the j omega t. Okay. Once again, as we proceed, we see that the equivalence only is increasing and increasing. There is no big deviation between what we saw in the case of transmission lines and electromagnetic fields at all. All right. Now, we have talked in length about this electric field. Okay. Let us write down the equation for del cross E, right. Okay. We are considering a time harmonic case, or a case where the source is periodic in time, all right, which means that you can also write down the right hand side of your equation to have a j omega mu h. Previously, we would have written this down as minus mu dou h dou t. h is now h e to the j omega t, all right. So, a derivative will become j omega mu h. Okay. Now, we can write down the left hand side. So, x hat, y hat, z hat, dou by dou x, dou by dou y, dou by dou z, Ex, Ey, Ez should be the most general way of writing down the left hand side. We already know that we can cross out dou x by dou by dou x and dou by dou y because the propagation direction is along z, and there is no way you can have Ez, you can cross that out. Ey we have assumed it to be 0, we are having only Ex, okay. It's the condition that we have posed, okay. And the right hand side is minus j omega mu h. This means that I can write down the left hand side, all right, to be y hat, okay, minus dou by dou z of Ex, y hat, oh it is minus y hat times minus dou by dou z Ex okay, is equal to j omega mu h, which already tells you that the direction of the magnetic field can only be y, because on the left hand side I have the unit vector for y direction. We already know that the magnetic field is going to have only a y component, all right. And we can write down now an expression, because now we have a solution for Ex, okay. We can always plug that solution over here. The general solution is what we will plug in over here to find out what the general solution for h is going to look like, okay. So, we can just write this down as minus j beta Ex plus e to the minus j beta z. So, I am doing dou by dou z of the general solution. The general solution that we have written is Ex plus e to the minus j beta z plus Ex minus e to the plus j beta z. Okay, we are taking dou by dou z for that. So, that becomes minus j beta Ex plus e to the minus j beta z, okay, plus j beta times Ex minus e to the plus j beta z, and this has to be equal to minus j omega mu hy, okay. I have dropped the vector terms because I am just equating y component to y component, okay. So, I just want to equate the y component to y component. So, I am just taking the coefficient of the vector unit vectors and I am just equating whatever is corresponding to y hat on the left hand side should be corresponding to y hat on the right hand side, okay. This we can make some rearrangement and write down the expression for the magnetic field, right, is going to look like, so minus j can be cancelled on all the left and the right hand side, and you can start to write down an expression for hy saying that it will have beta divided by omega mu. So, I am just bringing the right side to the denominator, right. Ex plus e to the minus j beta z minus beta divided by omega mu Ex minus e to the plus j beta z. We again notice the similarity only keeps adding up and adding up and adding up. When we had the expression for the current in the case of transmission line, the forward current was having a positive sign, the backward current was having a negative sign. Once again, now we are dealing with magnetic field, unit is ampere per meter, forward magnetic field seems to be having a positive sign, backward magnetic field is having a negative sign. So, the correspondence is only increasing and increasing and increasing, all right, and we can now write down that there is going to be a forward characteristic impedance and a backward characteristic impedance. So, you can take H, the characteristic impedance, the way we have to now define is Ex plus divided by Hy plus, okay, you can always substitute for Ex plus and Hy plus, okay, and you can see what is the value that you are getting, alright. For the backward case, alright, you will end up getting a negative sign identical to the case with transmission lines. The negative sign does not mean that you are having a negative intrinsic impedance, just means that the direction of travel is reversed, okay. So, the similarity keeps on increasing, okay. Now, the beginning of the class we said that we are going to look into an aspect which is not very similar. So far we are just strengthening the similarity too much, okay. What is the dissimilarity and what are we going to do about it, right? So, this configuration where you have electric field x component, magnetic field y component and the direction of travel to be z component resembles the fingers in your right hand, alright, where you hold your thumb, index and middle fingers orthogonal to each other, okay. The direction of travel is given by your thumb, the direction of your electric field is the index, alright, and the direction of the magnetic field is the middle finger, okay. And you can point it to one direction and say that this is the z direction. So, for all practical cases we will say that we will use x to be like this. We are used to drawing xy graphs where x is like this, y is like this and the z is pointing out of the plane. That is how we always look at it. Now, one of the things that you can easily figure out is as you rotate your wrist, alright, while keeping the direction that your thumb is pointing to be the same way, you can notice that you can rotate the electric field, the magnetic field will rotate itself by the same angle, but the direction of travel remains the same, okay. This actually means that if you fix the horizontal axis to be x, the vertical axis to be y, it is not mandatory that you should have propagation in z direction only for Ex and Hy. You can also have anything in between. You can have a component of electric field along x, component of electric field along y. Correspondingly, your magnetic field will have a component along x and y, and you can keep rotating, and this means that your direction of travel is still going to be the same. This is something which is different from your transmission lines, okay. So, you could have electric field having components in x and y, but remember that electric field cannot have a component in z, okay. Under no circumstance your finger is going to point towards this, you are rotating everything in plane. The electric and the magnetic field lie in the plane perpendicular to the direction of travel, and one of the terms that is used for these waves are plane waves, okay. So, here we can say that in the most general case, right, the electric field can be decomposed to Ex and Ey. When you do that, that means that the equivalent is you are rotating your hand by keeping the direction of travel fixed. When you move away from the horizontal axis, you can always take a projection of the index finger on the horizontal axis, projection of this on the vertical axis, you will get Ex and Ey. Correspondingly, the magnetic field can be decomposed to Hx and Hy, okay. But you will notice that always you will be decomposing them into Ex, Ey, Hx, Hy, etc., but never have a component in z direction, okay. Now, the direction of travel is referred to as the longitudinal direction, okay. That is the direction of length, okay. If your point A is here, point B is here, the distance, I mean the line that is connecting them is here, if it is your direction of travel, we call that as the longitudinal direction. What you can do is if you have a source on one place and receiver on the other place, you can point your thumb towards from the source to the receiver, and you will notice that the electric and the magnetic fields are going to be perpendicular to this direction of travel or perpendicular to the longitudinal direction, okay. So, the electric and the magnetic fields are going to be having only transverse components, Okay. So, the term that we use is transverse component, it is perpendicular to the direction of travel, it will always lie in the plane perpendicular to the direction of travel. So, these kinds of waves where the electric field is perpendicular, magnetic field is perpendicular to each other and to the direction of travel are known as transverse electromagnetic waves, or simply put TEM waves. Okay. So, okay. More generally, one can also say that if I know the value of electric field, for example, if I know that electric field is having an x and a y component, all right, one can quickly calculate at least the magnitude of the magnetic field. Let us say it is square root of hx square plus hy square. Okay. This can be written as Ex or Ey by eta square plus Ex by eta square. Note how it has been written, these things you will have to start thinking about it. Okay. We had hx square plus hy square, okay, but we have written Ey divided by eta, Ex divided by eta. Okay. We did not write it the other way around. So, there are some things that you will have to think about. Okay. Okay. Yeah. If one writes like this, you can just say that the magnitude of the magnetic field is going to be magnitude of the electric field divided by the characteristic impedance, which is similar to the magnitude of the current being equal to the magnitude of the voltage divided by the characteristic impedance. Okay. This gives you the magnitude. Okay. Now, we are going to talk about the direction. Okay. Now, there are many cases, right. You can have the electric and the magnetic field pointed in the same way at all points in space. Okay. You could also have, for example, with respect to time, in a particular point in space, you could observe different things happen. It is quite possible that at some instant of time, you are having Ex, Ex, Hy and Z like this, all right, or like this is how we usually, and maybe at another instant of time it is like this, maybe at another instant of time it is like this, maybe at another instant of time it is like this. All of these are valid as long as your direction of propagation is still pointing to the same side. So, it is quite possible that at a given point in space, with respect to time, the fields can go along the plane, right, they can rotate about the plane, right. So, it is quite possible, and if it is possible, all right, what do we call that? How do we distinguish between at some instant of time, if the wave is like this, all right, and at all instants of time suppose it is like this, we have to distinguish that from another wave where the direction of travel is like this, but it is doing this periodically with respect to time. We need to distinguish. So, what we do is we use the term known as polarization. Okay. So, broadly it is defined as temporal evolution, all right, or the time evolution of E field at a given location in space. At a given location in space with respect to time, what happens to the direction of electric field is called as polarization. Okay. Now, we need to look at this a little bit more closely, because this is something very different from the transmission line case. Most of them were similar, most of the properties were similar until now, but now there is a new property that is coming into the picture. Okay. In the case of transmission line, we just had what is known as polarity, we never had polarization, right. So, here we are having polarization, and we are also saying that at given location in space with respect to time, it could be doing this, but still the direction of travel is pointing in the same direction, right. So, what are all the possibilities, all right, and what are they called is what we are going to be seeing now. So, we will start with a general case and then make it more specific. Okay. Once again, we are always assuming here plus z to be the direction of travel. Okay. We are having a very general case where you could have Ex, where you could have Ey also, okay, because you are breaking down the electric field into some two components in the plane perpendicular to the direction of travel. So, the most general case you will have some component Ex and Ey. Okay. So, you can just write these down, all right, to be periodic. You can say that this is say real part of some value Ex naught magnitude, right, e to the j omega t minus j beta z, right. Previously we had Ex e to the minus j beta z. Now, I am including the effect of time because I want to know the temporal evolution of the electric field. So, I just multiplied with e to the j omega t, then the power of the exponent becomes j omega t minus j beta z. You could also write this down as j times omega t minus beta z. Okay. So, in this expression Ex naught will determine your amplitude or magnitude, all right, it is just magnitude, okay, and omega t minus beta z will be known as the phase. Okay. So, the phase is omega t minus beta z, magnitude is Ex naught. Okay. And since we are dealing with Ey in a similar manner, we can write down it has some magnitude Ey naught, okay, and you have e to the j omega t minus e to the minus j minus e to the j beta z okay, I think it is minus j beta z. Oops, in fact I have to multiply. Okay, had to multiply, but I added the term. So, e to the j omega t minus j beta z. Okay. So, once again we can look at the same configuration and decide whether this is the most general case or not. Okay. Now, your direction of travel is in one way, electric field is rotated, all right. It is quite possible that both the components x and y for the electric field may have the same phase or may not have the same phase. This is something to think about, all right. So, we have written Ey naught e to the minus e to the j omega t minus j beta z. In this case, both of the phase are identical, okay, but it is not necessary. All we are worried about is the resultant electric field composed of these two components has to point towards your index, but it is not necessary that they need to have the same phase at all. Okay. So, you could have Ex and Ey in the most general case out of phase, and the resultant could still be pointing in this direction. Okay. So, the better way to write this is actually to say that the most general case you could have a phase difference between Ex and Ey, and it is the most general case. Okay. Okay. So, you could have Ex and Ey out of phase, and the resultant should be having some magnitude pointing in the direction of your index finger, that is all. Okay. Now, we can say that similar to your electric circuits, you can say that phi, if it is positive, we already know that Ey will lead Ex by phi. Okay. If phi is negative, you can say that Ey lags Ex by phi. Very similar to AC circuits, where you will have some phase between voltage and current. You will say voltage lags current, current lags voltage, etc. Similarly, just say that Ex and Ey can have a phase between them. So, if we have to write down the expression for the electric field, right, you can always write this down as cos omega t x hat looks like. Now, one may notice that I have not included space over here. It has to be omega t minus beta z, correct? The most technical sense, the real power has to be omega t minus beta z. The way we have defined the word polarization is at a given space, we are trying to find out the temporal evolution. At a given space means that I have to assume a point and then observe that particular point at all instants of time. The simplest point that I can observe is z equal to 0. If I make z equal to 0, I get rid of one term, so I can focus on the remaining terms easily, alright. So, now I am focusing exclusively on z equal to 0, so I remove some terms, alright. So, it becomes Ex naught cos omega t x hat. The simplest place where I can observe is z is equal to 0, alright. So, the electric field looks like Ex naught cos omega t x hat plus Ey naught cos omega t plus phi y hat, and now I have a simpler equation to consider rather than having the space also. Okay. So, at point z equal to 0, I am going to be observing what is happening with respect to Ex naught, Ey naught, and what happens to the electric field in general. We can also use some basics of trigonometry and write down that in this case cos omega t is simply defined as Ex by x naught okay, and sin omega t, you can write this down to be square root 1 minus Ex by x naught square. So, 1 minus cosine square under root. Okay. Similarly, you can write down Ey by Ey naught is cos omega t plus phi. You can use some trigonometric identities. Cos of a plus b, you can use the formula cos omega t plus phi. So, you can write this down as cos omega t cos phi minus sin omega t sin phi, right. Okay. This means that I can write down the expression as Ex by Ex naught cos phi minus square root 1 minus okay. It's some steps, mathematical steps I have skipped, okay, but I think overall at this stage you should be able to follow what's going on, right. So, I am just written Ex by Ex naught cos phi minus square root 1 minus Ex by Ex naught square sin phi. Okay. Now, there are a few things that we can do. One of the things that we can do is start to look at mathematical manipulations of these terms and try to see if there is some relationship between Ex, Ey, Ex naught, Ey naught, etc., and try to see if we are getting an equation for something that we are able to follow. Okay. So, one of the things that we can do is okay, we can take two sides, all right, of an equation. We can say that cos square phi, if we are able to find out, sin square phi, if we are able to find out, cos square phi plus sin square phi is equal to 1, all right. Can I use this trigonometric identity to establish some relationship between Ex, Ey, Ex naught, Ey naught? This is some question that we can think about, right. So, I know the phase is phi, right. So, cos square phi plus sin square phi should be equal to 1. Can I use this equality to establish some relationship between Ex, Ey, Ex naught, Ey naught, etc. So, you could just say, if I am able to find out what is cos square phi plus sin square phi is equal to 1 and write this down in an equation form. So, I can write down what cos square phi is going to be like, what sin square phi is going to be like. Then I can substitute and I can have an equation for Ex, Ey, Ex naught, Ey naught, etc. Okay. So, I can do this and you can use the relationships that we have prior to us, all right. So, we can, I will just write down the equation and then spend some time on the interpretation of the equation. So, I will have Ex by Ex naught the whole square minus 2 Ex Ey cos phi by Ex naught have obviously skipped steps, but you can fill it up by yourself, right. Cos square phi plus sin square phi is equal to 1, right, and we are using this to arrive at a relationship between Ex, Ey, that is all we are trying to do, and we will spend some time on the interpretation rather than the equation itself, right. So, let us say that I have some equation and I want to find out what it means, and I then start to look at different cases, right. The first case that I look at is Ex is not equal to Ey okay, and say the phase between them is 0. Okay. In other words, the way we have written, we have Ex, Ex naught, etc. So, the way we have written, this means that Ex divided by Ex naught is equal to Ey by Ey naught. Okay. Let us take this particular case, right. Or you could also write this down as, if I know Ex, I could write this down as Ey naught by Ex naught times Ex. So, this resembles y equal to mx, okay, which is the equation of a line that passes through the origin. Okay. What does this mean? This means that Ey is always a constant multiplied by Ex. Okay. Ey is always a constant multiplied by Ex. So, instead of looking at all these things, you could look at the configuration that you had, right. You are having net electric field like this, the y component is always a constant multiplied by the x component. Okay. Now, we know that a constant will not change the direction at all. Okay. A constant will not change the direction, a constant will not change phase. Okay. So, it means that if I decompose this electric field to having an x and a y component, the phase of the electric field in the x direction is going to be the same as the phase in the y direction, because I am going to be multiplying by just a constant, only the value will change. If I had 1 volt per meter, maybe I had 3 volts per meter, all right, but the phase does not change, they are always in phase. So, Ex naught, I mean the x projection and the y projection will always be in phase. So, even with respect to time, it means that, all right, if I have something like this at some instant of time, at another instant of time, I can draw the projection, and still I will find that the projection is such that Ey and Ex have a constant multiple between them. it's always a constant. Okay. If that is the case, at any point in time, if I know the value of Ex naught, I will be able to figure out what is the value of Ey and the direction of Ey also by just multiplying it with Ey naught divided by X naught. Okay. So, this kind of a scenario, right, where your y component is a constant times x component, all right, of the electric field is known as linear polarization. This also means that there is no phase between Ex and Ey, they are oscillating with the same phase. Imagine that your electric field is oscillating, it's a time dependent electric field source. That means if you draw the projections at some instance of time, it will go like this, all right, it will reach a maximum, then the arrow will shrink, it will go to 0, then it will go to minimum, and then it will keep coming to 0, and it will be doing this periodically. All right. This is going to be how your x component is doing things. The y component is just going to increase, go to 0, decrease and go to 0, etc. But they are going to be doing this at the same time. That is, if your x is increasing, y is also going this, and then at the same instant of time they will do this, and then it does this. That means there is no phase difference between them. Okay. But the peak values that they can reach could be different. All right. You can have, for example, x going this much, and at the same time y is going this much, but then they meet here and then they cross, etc. Okay. So, there is no phase difference between them. The phase difference means that Ex and Ey will pass through the 0 points at the same instant of time. Okay. But with respect to time, Ex is oscillating like this, Ey is oscillating like this, all right. They will pass through the 0 at the same time. Okay. That is meant by having a no phase difference between your x and the y component of your thing. What is Ex naught? Ex naught is, since your electric field is doing this, the peak value that your x component of the electric field is reaching is Ex naught. And if you multiply that with your cosine omega t, then you will get the time dependence of this doing in the horizontal direction. That is all. Okay. Ey naught corresponds to the peak of the electric field of the y component, it does this. So, I will just mark this as Ey naught. Okay. So, Ex naught, Ey naught, etc. are very simple. If you know with respect to time, the electric field is actually oscillating like this. So, the x component is doing this, y component is doing this, but they arrive at the origin at the same instant of time, which means that they do not have any phase, but they could have different values. All right. They could have different values. Now, one of the things that a person can do is try to see, okay, at all instants of time, what shape describes this kind of polarization, right. That means that at every instant of time, you will take an x component, you will take a y component, you will draw the resultant. Okay. Now, for the resultant in this case, it is going to point in this direction, correct. The resultant is going to point in this direction. What will happen at another instant of time is, say the arrow has decreased, this arrow has also decreased in value. The resultant is going to be smaller, but it is going to point in the same direction because Ey is equal to constant times Ex, all right. The resultant has become smaller, but the angle it makes with respect to the x axis is the same. Okay. Then what happens? You reach the 0 point, both of the Ex and Ey reach the 0 point at the same time, resultant is 0. Okay. For a vector of length 0, you cannot determine the angle, so you forget about it, and then you see what happens more at some other instant of time. It is only correct that your electric field x will switch direction, all right, to a small value, but since your y component is a multiple by a constant, it will also switch the value, switch the direction, right. So, it will be like this. The resultant will then be like this, okay, and then your electric field x component will increase in value correspondingly your y will increase in value, but this is going to now be like this. Now, if you take this all together and try to draw for several cycles of time, what will happen, alright? If I take an xy axis like this, the resultant will go like this all the way, and then we will trace this path back. Oops. Right, it will pass through the 0, okay, and then what will happen, this thing will keep going like this. Remember that the red and black are co-located, just for the sake of clarity I am drawing like this. So, it will go like this, it will come back. So, the locus of all the points that the resultant will sweep with respect to time is a line. Okay. So, a linear polarization is actually very tough to imagine from the way we have written the equation, etc. Okay. But a linear polarization just means that your y component is going to be a constant times x component at all instants of time. So, the resultant, if your x component is 0, y component is also 0. Okay. If your x component is maximum, y component is maximum, but the values need not be identical because you are multiplying with a constant. If your x component is negative, y component is also negative. So, you will go between the first quadrant and the fourth quadrant, but you will not go to the other two quadrants at all. Okay. So, if you are assuming that the Ex is going to be positive, then you will be having always first and fourth quadrant only, you will not be going to the other quadrants easily. Okay. So, the resultant with respect to time in the space makes a line. Okay. So, this is known as linear polarization. This line could be aligned in any way perpendicular to the direction of travel, but with respect to time the resultant is always along a particular line. This is known as a linear polarization. You should be able to visualize. What we will do is we will also write a simple program to just make this concept clear, because the equation, the way in which we are deriving, is slightly complicated to imagine. Okay. So, it will be easier to just see pictorially what is happening by plugging in those equations and then seeing what it sweeps with respect to time. Now, since we have done this, we also realize that there are other possibilities. It is not always necessary that this is the only locus that is possible. There are other things which are possible. We will see them in the next class, but what we will do is we will write a program. Okay. And then what we will see is we will vary Ex, Ey with respect to time and then try to plot the resultant. And then you will realize what is what. Okay. Of course, many of you would have guessed there is something known as circular polarization, elliptical polarization and all that, but we will arrive at that through the program rather than doing this first. Okay. Because this may become confusing, because there is Ex, Ex naught, Ey, Ey naught, etc. So, people will start getting confused as to what is happening. Okay. So, but once you see the program, things will start to register. What is meant by Ex, what is meant by Ex naught, all these things will become very, very clear. What is meant by phi, everything will become clear. Okay. So, I will stop here.